Gradient descent is a fundamental optimization algorithm used in machine learning to minimize a cost function. The goal is to find the set of parameters that minimizes the error, allowing the model to make accurate predictions. This cost function represents the error between a model's predictions and the actual values. For example, in linear regression, we might use the mean squared error. We can visualize the process of gradient descent as navigating a landscape, trying to find the lowest point. The lowest point in this landscape represents the optimal set of parameters for our model. However, the landscape might have multiple valleys or local minimums. Gradient descent works by iteratively taking steps in the direction of steepest descent. Let's break down the process. First, we start at a random point in the parameter space. Next, we calculate the gradient, which tells us the direction of steepest ascent. Then, we take a step in the opposite direction, the direction of steepest descent. Finally, we repeat this process until we reach a minimum or convergence criteria is met. In this three-dimensional representation, we can see arrows pointing in different directions. The gradient points in the direction of steepest ascent, so to minimize our function, we move in the opposite direction. Gradient descent is used in numerous machine learning algorithms, from simple linear regression to complex neural networks and deep learning architectures. To summarize what we've learned about gradient descent, next we'll explore the cost function and loss surface in more detail. The cost function is a measure of how well our model performs. It quantifies the error between our predictions and the actual values. Imagine a 3D bowl-shaped surface. This is our loss surface, where the height represents the cost function's value for different parameter settings. The lower the point on the surface, the lower the error. Our aim is to reach the bottom of this bowl, which represents the optimal parameters for our model. In gradient descent, we start at some point on this surface and iteratively move downhill to find the minimum. The shape of this surface depends on our model and the data. There are different types of cost functions used in machine learning. The choice depends on the type of problem we're solving. Mean squared error, or MSE, is the average of the squared differences between predicted and actual values. It's commonly used in regression problems. Cross-entropy loss measures the performance of a classification model whose output is a probability value. It increases as the predicted probability diverges from the actual label. Here's a comparison of entropy loss and MSE loss. Notice how they behave differently as the predictions change. Choosing the right loss function is crucial for effective learning. Understanding the cost function and its corresponding loss surface is fundamental to gradient descent. It guides the algorithm toward finding optimal model parameters. The core of gradient descent is the update rule. This formula tells us how to adjust the model parameters in each iteration. Let's break down each component of this formula. In gradient descent, we're trying to find the minimum of a cost function, which can be visualized as a surface. Gradient descent is an iterative algorithm that progressively moves toward the minimum. With each iteration, we take small steps downhill, guided by the gradient. The gradient points in the direction of steepest increase, so we move in the opposite direction to minimize the cost. For a model with one feature or multiple features, we update each parameter simultaneously. This process continues until we reach the minimum of the cost function. At this point, our model parameters have converged to their optimal values, minimizing the prediction error. The learning rate, denoted by alpha, is a crucial hyperparameter in gradient descent. It controls the size of the steps we take during each iteration of the optimization process. In the parameter update rule, the learning rate scales the gradient to determine how much we adjust our parameters. Let's examine how different learning rates affect the optimization process. With a large learning rate, the algorithm takes big steps, potentially overshooting the minimum. This causes oscillation around the optimal value, and in extreme cases can lead to divergence. Conversely, with a small learning rate, the algorithm makes steady but slow progress, taking many more iterations to reach the minimum. To understand this better, Let's visualize gradient descent on a simple quadratic function. With a learning rate that's too large, we take big steps that cause us to overshoot the minimum. With an optimal learning rate, we make steady progress toward the minimum, converging efficiently. In more complex optimization landscapes, the impact of learning rate becomes even more crucial. Here we see the atom optimizer with different learning rates navigating the Beal function. When selecting a learning rate, start with a common value like 0.01 and adjust based on model performance. If your model learns too slowly, try increasing the learning rate. If it oscillates or diverges, decrease it. Adaptive learning rate methods like ATOM can automatically adjust the learning rate during training, making optimization more efficient and reducing the need for manual tuning. Batch gradient descent is an optimization algorithm that uses the entire training dataset to compute gradients at each iteration. It uses the entire training dataset, all M examples, to compute the gradient and update parameters at each step. Batch gradient descent offers several advantages. It provides stable gradient estimates, leading to a smooth convergence path. With an appropriate learning rate, it's guaranteed to converge to at least a local minimum. However, it comes with significant disadvantages. It's notably slow for large datasets, as it requires calculating gradients across all examples before each update. It also has high memory requirements and can't efficiently handle streaming data. Let's visualize how batch gradient descent works on a loss surface. Here's a contour plot representing a loss function. The center represents the global minimum we're trying to reach. The batch gradient descent path is characterized by a stable, smooth trajectory towards the minimum. Each point represents a complete pass through all training data. The computational cost of batch gradient descent can be significant. Each iteration requires processing all training examples, making it expensive as datasets grow. For large datasets with millions of examples, this becomes impractical. This simplified implementation shows how batch gradient descent processes all examples in each iteration. Note how we compute the gradient using the full dataset before making a single parameter update. To summarize, batch gradient descent offers stable and smooth convergence by using all training examples in each iteration. However, this approach becomes computationally expensive and slow for large datasets, making it best suited for smaller problems or when convergent stability is critical. Stochastic gradient descent, or SGD, is a variation of gradient descent that processes just one training example at a time. Unlike batch gradient descent, which uses the entire dataset for each update, SGD computes the gradient using just a single training example. The update rule shown here adjusts parameters theta using the gradient computed from just one data point at each iteration. This approach has several key characteristics. Let's visualize how SGD works. This contour plot shows a loss function with the minimum at the center. The orange path represents how SGD moves through the parameter space. Notice how the path zigzags toward the minimum. This erratic behavior comes from using different individual samples for each update, introducing variance into the process. This diagram illustrates an interesting property of SGD's noise. While batch gradient descent follows a smoother path with low noise, SGD takes a more chaotic route with high noise. Batch gradient descent can get stuck in a suboptimal solution, following the blue path to a so-so outcome. In contrast, SGD's noisy updates, shown by the red path, can help escape local minima and find better global solutions. Let's examine the advantages and disadvantages of SGD. On the positive side, SGD offers much faster training times and lower memory requirements, since it processes only one example at a time. It can also escape local minima due to its noisy updates, and it updates parameters more frequently, making it suitable for online learning. However, SGD suffers from high variance in parameter updates and noisy convergence behavior. It may never settle exactly at the minimum, often requires learning rate adjustments, and is generally less stable than batch methods. To summarize, stochastic gradient descent processes one training example at a time, making it much faster than batch methods, but introducing noise into the optimization process. This trade-off between speed and stability makes SGD a valuable optimization method, especially for large datasets, and it serves as the foundation for many advanced optimization algorithms. Mini-batch gradient descent processes small batches of the training data in each iteration. Let's compare mini-batch gradient descent with batch gradient descent and stochastic gradient descent. As you can see, mini-batch gradient descent offers a balance between the stability of batch methods and the speed of stochastic gradient descent. The update rule for mini-batch gradient descent computes the average gradient over a small batch of examples. Mini-batch gradient descent offers several advantages that make it the preferred choice in most practical applications. When comparing the convergence paths, we can see that mini-batch gradient descent offers a smoother descent than stochastic gradient descent, while still converging faster than batch gradient descent. In practice, choosing the right batch size is important. Too small and training becomes unstable, too large and you lose the computational benefits. Typical mini-batch sizes range from 32 to 256 examples, though this can vary depending on the problem and available hardware. Advanced optimizers improve upon standard gradient descent by addressing several key limitations. Basic gradient descent faces challenges, including slow convergence in ravines, using the same learning rate for all parameters, and getting stuck in local minima. Momentum helps accelerate gradients in the right direction by accumulating a velocity vector. The parameter gamma controls how much past gradients influence the current update. RMSprop and AdaGrad adapt the learning rate for each parameter based on the history of gradients. They divide the learning rate by the square root of accumulated squared gradients, allowing faster learning for infrequently updated parameters. Atom combines the advantages of both momentum and RMSprop. It maintains moving averages of both gradients and squared gradients, enabling faster convergence and better navigation of complex loss landscapes. Let's compare how these optimizers perform. This visualization shows the paths taken by different optimizers as they converge to the minimum. Notice how Atom, in red, finds a more direct path than the others. This graph shows the training cost versus iterations for different optimizers on a neural network task. Atom consistently achieves the lowest training cost, while AdaGrad converges more slowly. The logarithmic scale highlights the significant performance differences. Advanced optimizers can be further enhanced with techniques like batch normalization. This visualization compares optimizer performance with and without batch normalization. Notice how all optimizers benefit from batch normalization, but some gain more advantage than others. To summarize, advanced optimizers significantly improve upon basic gradient descent. Momentum accelerates convergence, RMSprop and AdaGrad adapt learning rates per parameter, and Atom combines the benefits of both approaches. For most deep learning tasks, Atom is a solid default choice, offering excellent performance with minimal tuning. All optimizers can benefit from additional techniques like batch normalization.